transition here, the realm of who decides what goes into a register and then what gets kicked out of registers and goes beyond that, that's up to the compiler. So we're kind of just working up to the data that is closest and inside the CPU all the way out to the so-called cloud, or data that is way out there somewhere in the database. So who decides what data comes into and out of registers is the compiler. So we move on from there. The cache is not big enough to store all of the information that you would ever want to process, obviously. So beyond that is main memory, or DRAM. And that is still not enough, as you hopefully know or suspect. So if you have to go past DRAM, you go to the disk. And maybe it's not actually a disk, maybe it's an SSD, but disks are still used today in data centers and in desktop PCs. And deciding when data gets kicked out of DRAM and goes to disk is the OS's job. Okay, so this is kind of the picture of data that we have so far, at least assuming you've kind of gone through the normal career path in CS, taken some programming classes. This is your view of data. So all of this is, some of it's up to the compiler, some of it's up to the OS, but all of this, as a programmer, you have to be aware of how all of this works. How and when does the OS decide to move data out of RAM and onto disk, or off of disk and back into RAM? At least in order to be a really effective programmer, you have to know how all of that stuff works. And there are various classes you maybe haven't taken yet that go into the details of that. This class will be one of them that starts to go into those details. Okay? So this is the picture of data we have so far. But then beyond that, you take that whole thing, and you have a computer or a smartphone or something with a CPU and RAM and a disk or some kind of solid-state storage, and you go out and access a server somewhere. So maybe it's Google or Facebook or Canvas or whatever. But those servers, those things over on the right, those are also just computers. They have CPUs and memory and disks. This is where the challenges that this class starts to address come into play. How do you manage data when there is so much of it that there's no way it's going to fit in this little realm? And so just, let's look at Google. Let's say you go and try to log into Google from your computer. It has to go and look through the billion or several billion or however many accounts it knows about. It has to check your login credentials, load whatever information you're trying to load for your one little account among all the billions that it knows about and all the terabytes upon terabytes of data that it has. So that's kind of where the challenges start to get different. And to make this even more interesting, those servers sometimes talk to other servers. So like Canvas, when you go in to log into Canvas, it's going to go talk to Amazon, AWS, to get more data about your class or your grades or whatever. And that's just another computer. That's some server that's running some database and listening for network connections. Okay, so now in this class, all of this realm is still programmer managed. Luckily there are database systems that exist that lots of smart people have figured out over the years, but you as a programmer, you still have to know what they are capable of, how to use them effectively. So that's this class. You're not going to make your own database system. You're going to use one to store data that represents and solves some problem. So we're not implementing MySQL, we are using MySQL. Thankfully, lots of smart people have figured out how to make MySQL already and other database systems. So this realm, this end of the spectrum, the so-called big data end of the spectrum, has its own challenges that are not really present in these little small local programs you write that just kind of use the disk and RAM. Vast amounts of data, and we have to be able to quickly access, combine, and filter that data to get to what's interesting. I don't care about all of the other billion Facebook users unless I'm some malicious attacker. I care about my Facebook account. Has to be available online always, robustly, securely, to however many millions of users are out there accessing Facebook at any given time. Okay, so let's start to think about why this is hard, or how would you go about saving a billion user accounts? So let's say you want to save a bunch of student information to a file. So option one is you just write some basically English text to a file. All the information that we want is there. So what we want is like the student's name, major, GPA, but then there's all this extra cruft in there that a computer doesn't need, all these English words that a computer doesn't need. So how would you search for a particular student if you stored data this way? Well, you would have to know kind of like which keywords to look for and how the sentence is structured. And even then, even if you knew that, you would still have to essentially scan the entire file, which could be terabytes or more, in order to find any particular student, like when they're trying to log in. So obviously, we don't do that. Better is get rid of all that like English cruft words and store it in something like JSON. So this is called self-describing data, because the data includes not only the values you care about, but the data includes a description of itself. So it has this thing, major colon. So that is included in the data, and it means the thing coming after the colon is something called major. And this isn't actually JSON. I'm missing a ton of curly braces if this was going to be JSON, but essentially same idea. There's the name of the field and a colon and the value of the field. Same question though. How would you find all students enrolled in whatever class? Or how would you find a student with a certain name? If all you had was a big text file containing this self-describing data, one record after another, you'd still have to do a linear scan through this gigantic file. At least you know what you're looking for now. You can look for, if I'm looking for name, then I can just look for name colon, and then move to the next record if it's not the right one. But not going to scale to large data. Other techniques you might be familiar with, something like XML. Essentially, this is just like another form of JSON. It's self-describing data. It has tags and values. So unless it's ordered in some particular way, this doesn't really solve the problem of massive amounts of data. How do you find one particular record you're interested in? And let me expand on that actually a little bit. So I said unless it's ordered in some particular way. Let's say it is ordered, and like you can do a binary search on student's name. Okay, great. So you can find a student quickly. But then what if you wanted to find all students enrolled in a certain class? Well, if the data is ordered by student name, then it's not ordered by class, and you're out of luck. So you can order it to support one type of search that you might want to do, but in these big data systems, we want to do many, many kinds of unpredictable searches, so this is not going to work. Stop me with any questions, by the way. I like classes to be as interactive as possible, so if you have any questions, just let me know. Okay. So let's try to address that problem. So I said, well, what if we sort it by name? Then we can quickly search by name. Let's, instead of sorting the entire file, let's just use a data structure. So you can put data into a data structure and then quickly find things, or you can sort it on some criteria and then quickly find things. Let's use a data structure. think way back to your algorithms class, 2420. So we want a data structure that very quickly supports adding, removing, and searching, and specifically also range queries. So something like find all values between some min and max, like all values between two dates. And we want to be able to just enumerate all of the things. What data structure is that? Yeah.
B-tree.
B-tree, okay. So you may not have seen B-trees in 2420. What is some other form of a data structure that people have probably seen?
A hash table.
Hash table, okay. Does hash table support all of these? It definitely supports add, remove, and search. Does it support range queries? No. So hash table won't do it. B-tree is right, but many of you probably don't know what that is.
Could you clarify a range query?
Range query. So find all things between some minimum and some maximum value. Yeah.
Heap.
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 So a heap does not quite support, doesn't really support searching for an arbitrary item. It supports finding the minimum or maximum. Yep, back there.
Binary search.
Binary search tree. Okay, thank you. Turns out this other answer, B tree, is another form of search tree, but just not binary. Binary search tree is probably the one you're familiar with. It's not actually really what a database uses. It'll use something called a B tree. So, good. That starts to solve this problem of like, well, we have structured, let's go back. We have structured data, and we want to be able to search for certain records based on some field quickly. Okay, well, we can build a binary search tree or some kind of search tree around those records. But now let's say not just students. I have tons of professors, courses, assignments, anything kind of associated with like a school or university. So let's start expanding on that a bit. We've decided that structured data is good. Something like JSON or just self-describing data where there are tags for the fields. So if we want to store students, professors, and courses, maybe I have 3 different files. Or maybe each of these boxes are just 3 different sections of some big file or something. So the students they each have a name. They have a list of classes that they're enrolled in. They have a GPA and an ID. Okay, so I have 2 students here. One of them's enrolled in a CS class and a physics class. One of them's enrolled in a film class. Professors have a name. They have what they're teaching. Courses have a name, a number, and a department. And we'll suppose each of these orange boxes is a separate file for now. Now, I might want to ask all kinds of various information about questions about this information, like find all courses that student Y is enrolled in. Okay, it turns out that's easy, the way I've drawn this. Can I draw it? Nope. Finding all courses a student is enrolled in is just included right with the student there itself, so that's easy. But what about finding all teachers of some student? So we'd have to go find the student first, then look at their classes. So, CS 5530 and Physics 2010. So we'd have to take those and go look in some other file. Okay, so I've found, a couple of classes, and then we'd have to take those. We're looking for who is the teacher. So we'd have to take those and then go look into the professor's records and find that. Okay. So, assuming we're doing something like this, how can we quickly, say, find all students enrolled in course X, find all teachers of a certain student, other queries that you can't really predict, but you might want to ask of this data. Order students by GPA, order courses by enrollment number. So enrollment number is not directly stored here, but you could infer it by doing some counting. Now imagine there are millions of each, so not just like 2 per file, and these operations all happen very frequently. Here's the solution. First, we need structured data. Structured data just means essentially it's tagged, kind of like JSON. You have the name of the field, you have the value of the field. But that's not the full definition of structured data, which we will get to right after this. We'll expand each of these. Then we need data structures to be able to quickly search through each of them. Then we need a query language. So that's the part where, how do I express these questions to a computer? I can't just say, computer, give me all, so-and-so. Not until Star Trek, anyway. But we don't have Star Trek yet. So structured data it's self-describing, meaning it's tagged, but it also means that every record has a specific set of fields called attributes. So a course, for example, has a department, which is a string. It has a number, which is an int, and it has a name, which is a string. So it's not just the name of the field, it's the type of the field. And every course has to have exactly these 3 things. A course cannot have more than this. A course cannot have less than this. So that's essentially structured data. It makes it just way easier for computers to reason about data if the data is structured. It makes it easier for people, too, as it turns out. So just to kind of recap, unstructured versus structured. In English, we kind of, if I was describing a student, I would use an unstructured form. In a computer, I would use something like this. I would say, okay, there's a name, which is a string, and the name is Jane Doe. Okay, so that's number 1, structured data. And then storing the data. If we just put a whole bunch of JSON records into some file on disk, as we already sort of discussed, that's not going to work. So we need some kind of data structure. We store the data itself plus a structure around the data that allows us to quickly find the interesting parts of the data. So something like a tree or a hash table turns out both. Databases use both. So let's look at that a little more. So I have here 4 records, 4 students. They are structured. So every one of them has a name, a major, a GPA, and an ID. Okay, this is just the data itself, though. So imagine these are just in a file somewhere, just in some order. We don't even know what order, it doesn't matter. So if I wanted to find a particular student by name, and it was just this big file with a big blob of these structures, I could linearly scan through the file, and that would take forever. Or I could build a binary search tree where the nodes in the tree are not the records themselves. The nodes in the tree are just that key that I care about searching on, so just name. So look at the nodes here. All they contain is the name, and then the leaf nodes contain, or well, actually all nodes, the way I've drawn it, contain a pointer to one of the records. So this would be, in our example, if these records are just somewhere on disk, these pointers would just be like an offset into the file. That way I can quickly traverse this binary search tree to find, say, Tim, or whatever, find the location of Tim in a file, and then immediately go load that out of the file. Okay, great. Now, what if I want to find all students who have a GPA greater than 3.5? This binary search tree does not help. But I can just build another one. So here's a different BST, different structure, different keys. This one is built on the GPA key. And it has pointers going into records, but the shape of the tree is different. Where each node is pointing into the file is different. So if I wanted to find, something based on GPA, I would use that tree instead of this tree. So what we do is we store the data itself, the actual records, just store them in a file somewhere. Order is not particularly important because we additionally store a whole bunch of data structures. one that lets us quickly find by name, one that lets us quickly find by GPA. I could add another one based on major, another one based on ID. That one might actually be a hash table instead of a tree, but so you get the idea, hopefully. Yes? If two students have the same GPA, doesn't that mess things up? No, we're kind of leaving out some details here. You can have multiple students with the same GPA, store it efficiently in a search tree, and we'll kind of get to that later in the semester. It'll use this thing called a B tree, which supports that. But actually, that is a good point. So what I want to bring up now is, so what about the data storage cost of this? Like, how big is this all going to be? If I have to store all of the records and a whole bunch of trees, well, turns out the trees, as I said, they're not actually binary search trees. They're a different kind of search tree that doesn't actually need to store every single key. And turns out the overhead of storing these trees is not actually as big as you might be fearing that it is. Okay, so finally we need a language for expressing this stuff. That's the third part of the solution, is a query language. So you could write some kind of programming language code, C, Java, whatever. You could write some function like get students by GPA, and then you pass in a GPA and it returns all students with that GPA or whatever. And you would, inside of that function, you would query the appropriate tree with whatever value. Okay, great, that works. Then, you'd have to write another function for every other query you wanted to possibly run. Instead, we use something called a query language, which has these keywords like where and from that, it's not a programming language, but it lets us dynamically devise various queries. And so there's a compiler of sorts that converts this into a sequence of operations, querying those trees, loading records out of files to find the information you want. So this is, find all names of students from the students' records where their GPA is greater than 3.5. Okay, questions so far? Yeah.
Do each of those cells that were on the bottom that you'll actually be putting into the text, or into the orange cells, do they each have individual value descriptor keys, or are they all always going to contain name, major, GPA, and ID?
Do each of these records have all of this information? Yes. Every record has every piece of required information in the structured data.
Do you need to keep then the tags for each of those pieces of data?
The tags, yes, good point. So notice they all have something called ID. Do we need to keep the tags themselves, name, major, GPA, ID? No, that's just inferred. That's known. You only need to really store that somewhere because every record has the exact same structure. So you don't need to duplicate the tags themselves. Okay, so structured data plus data structures plus a query language is essentially a database system. So that is what it does for you, plus much more. So this class is all about how do we effectively utilize a database system to solve some problems, such as, let's say you wanted to make Canvas. Stores tons of information about students and classes and assignments, and it uses databases. So, luckily, there has been lots and lots of research into this topic, and they've figured it out pretty well. So we'll take advantage of all that research, and we will use MySQL, which essentially solves most of these problems. At least if you know what you're doing, it'll solve these problems for you. There are wrong ways to use MySQL, and we're going to learn how to use it the right way. Okay, so there are two parts to a database system. There's the database management system. That is, call it the engine, I guess. That's the actual program that's running on some server that figures out how to store the data and how to process your queries. So in our case, that is MySQL. And then there's the query language. In our case, that is SQL. That's like the interface to the engine. So you will write SQL queries, and then it's up to the engine to figure out what to do with those queries and how to store your data. Okay. So kind of just reiterating, like option one, as like a 1410 or 2420 level programmer, you would do something like write some Java program. The Java program uses the I/O library, and then the I/O library goes to the OS, which goes to the disk and saves your data in a file. What we will be doing is, you're still a programmer. There is programming in this class. But the code you write will use an SQL API, and then that will go and contact some database management system on a server somewhere, which will then talk to the OS and the disk and decide how to store your data. There are other ways to get to a database, though, not just through programming, and we will be doing essentially all of these. You can interact with it directly through the command line, just write SQL queries. You can use a workbench, which is like a UI version of, like a graphical version of essentially still the command line. But some people are just not comfortable without having a GUI. And then there are software systems that interact with the database. So although we won't actually be writing Overwatch, it would be fun, but you will write some software system that dynamically generates SQL queries and interacts with the database. Okay, so we'll talk about principles of structured data. And so this is even kind of like outside the context of SQL or any particular database system. We'll talk about just the practice and principles and theory behind structured data storage. It's called the relational model. One way of looking at this is called the relational model. Application of databases, from using it through the command line, using it in software, and then towards the end of the semester we will start to get into, well, how does the DBMS actually work? How do these trees work? How does it know how to execute a query, a certain SQL query? And you need to know enough about that to avoid using it ineffectively. So there's kind of a mix of theory and practice in this class. There's plenty of practical usage of databases, and you will produce a project by the end of it, but you will also understand the principles behind, like, how do you design a good system that stores structured data. Okay, so that's kind of the syllabus stuff. In these long classes, I like to take a break in the middle, so this is a good point to do that. Let's take a 5-minute break.